Task 3.5. Assess and mitigate the vulnerabilities of security architectures, designs, and solution elements. As we explore this task, remember the concepts we'll discuss here are interconnected and form a holistic security approach. If you find that I don't go deep enough, that's what the prompt on the last slide is for. All right, let's move. This one's a biggie. Yeah, this task has 15 subtasks, each focusing on different types of system or technologies. We'll explore everything from client-based systems to cutting-edge concepts like edge computing and serverless architectures. As we go through each subtask, you'll notice that many of the concepts overlap. The repetition is intentional and beneficial, as it reinforces key security principles that apply across multiple domains. The CISSP exam tests your ability to understand these interconnections and to apply security concepts holistically. 3.5.1 Client-based systems. I think you guys should understand what these are. Client-based systems are the end-user devices that access network devices and resources. Examples could include desktops, smartphones, pads, tablets, whatever, your watch. Security considerations. When it comes to client-based systems, the CISSP exam may test your knowledge on endpoint protection strategies, patch management processes, and access control mechanisms. Some of the top associated risks: be prepared to get questions about malware infections, data leakage, unauthorized access, and lost or stolen devices. Remember, client-based systems often serve as the initial entry point of interaction between users and organizational systems. Their security is crucial for the overall defense strategy. 3.5.2 Server-based systems. The exam will definitely include questions about these critical components. Definition: a server is any computer that provides services to clients on a network. Types: well, be familiar with all kinds of types: file servers, web servers, database servers, application servers, and mail servers. Some key features that the exam may test your understanding on server characteristics are high performance capabilities, scalability, and the ability to handle multiple concurrent sessions. Security measures: be prepared to discuss server hardening techniques, access control mechanisms, regularly patching processes, continuous monitoring strategies. Web application security. Definitely want to check out OWASP and keep on top of their top 10 risks that include injection vulnerabilities, broken authentication issues, and some top risks associated with these: unauthorized access, data breaches, denial of service, misconfiguration, and privilege escalation incidents. Remember, server security is interconnected with client security. The CISSP exam often presents scenarios that require you to consider how vulnerabilities in one area can impact the entire system. As we progress through the other subtasks, you'll see how server security relates to many topics like database systems and virtualization. 3.5.3 Database systems. Definitely a crucial area, crucial attack point. The definition is a database system is some system that stores, manages, and retrieves data in an efficient way. Types might include various things like relational databases, SQL, NoSQL, that means not only SQL, object-oriented databases, and distributed databases. Key components: be prepared to discuss the data storage mechanisms, query processing, transaction mechanisms, backup and recovery mechanisms. Security features: the exam might ask about database security measures such as access control implementations, encryption techniques, and data integrity checks. The top risks associated: SQL injection, data breaches, unauthorized access, data corruption issues, and improper access controls. It's important to note that interconnected nature of database systems with other elements we've discussed. For instance, a database server is a type of server, and they often interact with client systems. The CISSP exam presents scenarios that require you to consider these relationships and how vulnerabilities in one system can affect other areas. 3.5.4 Cryptographic systems. Definition: Cryptographic systems use some algorithms to secure information through encryption and decryption. The key components that you might understand or test your understanding of on the exam: encryption algorithms, key management practices, digital signature implementations, and random number generators. The types: be prepared to discuss the three basic algorithm types: symmetric, like AES, that encrypts the data; hashing algorithms like SHA that check the integrity of the data; and asymmetric algorithms that it can encrypt symmetric keys for key sharing or sign hashes for digital signatures. Remember, our asymmetric algorithms don't encrypt much, either just a key of maybe 256 bits for key agreement or a hash of 512 bits. Applications: the exam might ask about cryptography's role in secure communication, data protection at rest and in transit, authentication processes, non-repudiation when you digitally sign, remember. The top risks: well, focus on understanding weak key management practices, outdated algorithms, implementation flaws, and perhaps quantum computing threats if they ever do come about. It's crucial to recognize how cryptographic systems interact with other areas we've discussed. For instance, they play a vital role in securing client-based and server-based systems, as well as protecting the data in the database. It's all over the exam. 3.5.5 Operational Technology, Industrial Control Systems, or ICS. This is a very crucial area on the exam and in the real world. The definition: this is the hardware and software systems that monitor and control industrial processes, the physical infrastructure. Components that the exam might test your knowledge on: programmable logic controllers, SCADA, that's supervisor control and data acquisition systems, DCS, or distributed control systems. Key characteristics: you should be prepared to discuss real-time operation requirements, high availability needs, specialized protocols. And the security challenges: the exam might ask about legacy systems and their vulnerabilities, erosion of air gap protection, difficulties in implementing traditional IT security measures. Top risks associated: well, I would focus on understanding physical damage potential, production disruption impacts, safety hazards, and cascading failures in critical infrastructure. It's important to note how OT/ICS security relates to other areas we've focused on, and these systems interact with traditional IT networks, bridging the gap between cybersecurity and the physical world. The CISSP exam frequently presents scenarios that require you to consider these relationships and how vulnerabilities in one area can affect others. 3.5.6 Cloud-based systems, a very critical area for the CISSP exam. Definition: cloud-based systems are computing services delivered on the internet, offering scalability and on-demand service. The service models on the exam basically cover the three models of SaaS, software as a service, which provides access to software applications over the internet; infrastructure as a service, which offers virtualized computing resources on the internet; and platform as a service, which provides a platform allowing customers to develop, run, and manage applications. The deployment models that you'll be expected to know for the exam: public cloud, services offered by third-party providers for the public internet; private cloud, cloud infrastructures operated solely for a single customer; hybrid cloud, combination of public and private clouds, allowing data and applications to be shared between them; and multi-cloud, use of a multi-cloud computing services in a single heterogeneous architecture. Security considerations: key security aspects for cloud environment include shared responsibility model, defines the security responsibilities between the cloud provider and the customer; data encryption, protecting data at rest and in transit in the cloud; access management, controlling and monitoring access to cloud resources; compliance, ensuring cloud services meet regulatory requirements. Top risks: the major security risks associated in cloud include data breaches, that's unauthorized access to sensitive information stored in the cloud; Misconfigurations, that's vulnerabilities in the interfaces used to interact with cloud services. Account hijacking, unauthorized access to cloud accounts, often through stolen credentials. And vendor lock-in. This is difficulty in moving from one cloud provider to another due to proprietary technologies or formats. The exam emphasizes on understanding how these cloud concepts interact with each other and other security domains. 3.5.7 Distributed Systems. Definition: distributed systems are composed of multiple autonomous components that communicate and coordinate to appear as a single coherent system. Characteristics that the exam will cover: resource sharing. Multiple components share hardware, software, or data resources. Concurrency. System components operate simultaneously and independently. Scalability. The ability to handle growing amounts of work by adding resources to the system. Fault tolerance. The system continues functioning when one or more components fail. Some examples: the exam may include questions on various types of distributed systems, like peer-to-peer networks, systems where each node acts as both a client and server. Grid computing, a network of computers working together to solve a common problem. And blockchain systems. These are distributed ledger technologies used for secure, decentralized record keeping. Top associated risks. The CISSP exam addresses several key risks in the distributed systems, including consistency and synchronization issues. That's ensuring that all nodes have the same data at the same time. Network failures, the impact of network outages on system functionality. Security vulnerabilities in individual components, how a weakness in one part can affect the whole system. And complex attack surfaces, the increased number of potential entry points for attackers due to the distributed nature of the system. The exam often presents scenarios that require understanding of how distributed systems interact with other technologies we've discussed, such as cloud computing, IoT, and edge computing. 3.5.8 The Internet of Things, IoT. Crucial area on the exam, and definitely in real life. Definition: IoT refers to a network of interconnected physical devices that collect and exchange data through embedded sensors and internet connectivity. The applications that the IAC2 exam might cover will include smart homes, connected devices for home automation and security, wearables, personal devices that monitor health, fitness, or provide communication, industrial, sensors and devices used in manufacturing and industrial processes, smart cities, connected infrastructure for improved urban services and management, and connected vehicles, cars and other vehicles with internet connectivity and sensors. The key components: the exam may address 5 key elements of IoT systems. The sensors, the components that perform the actions based on, the devices that collect the information. The actuators are the components that perform actions based on what the sensor sensed. Connectivity, this means that the means by which the device communicates, and it's usually or very often wireless. Data processing, the system that analyzes the data and act on it. And then the user interfaces, methods for users to interact with and control the IoT device. Security challenges: the exam might highlight several security issues specific to IoT, including limited computing power. Many IoT devices have constrained resources, making traditional security measures difficult to implement. Vast attack surface: the large number of connected devices increases the potential entry points for attackers. Weak default settings: many IoT devices come with insecure default configurations. You just go to Google, what's the default password for? Difficulty in patching, updating firmware and software on IoT can be very challenging. And the top risks associated that the exam might cover: unauthorized access, attackers gaining control of these devices; data privacy breaches, unauthorized collection of exposed data; botnet exploitation. I remember the Mirai botnet. And then physical safety hazards, compromised IoT devices actually causing real physical harm. 3.5.9 Microservices. A very important topic on the exam and in real-world security. Microservice is an architectural style where applications are composed of many small independent services that communicate via APIs or application program interfaces. Probably the hardest challenge we have, and will get increasingly worse as we get more AI agents out there. Key characteristics that the exam will cover, well, several features. They're loosely coupled. Services are independent and deployable and can be developed in different programming languages. Independently deployable. Each service can be updated, deployed, and scaled without affecting other services. Organized around business capabilities. Services are defined by business needs rather than technological constraints. The benefits, the exam might highlight some of the good things. They scale well. They're very flexible, easier to update, provide individual component of an application. Easier maintenance, smaller focused code bases often make it a lot easier to change and maintain. And technological stack diversity, so different services can run on different technologies as needed. But the top risk that the exam will definitely hit you with: API security vulnerabilities. Weaknesses in the interfaces between the services can be and are very daily exploited. The increased attack surfaces. More services mean more entry points. Complex service-to-service communication. Securing interaction between the numerous services, very challenging. Data consistency challenges. Ensuring that data remains consistent across distributed services can also be difficult. The exam will often present scenarios that require understanding how microservice architecture interacts with other concepts we've covered, such as cloud computing, containerization, and distributed systems. 3.5.10 Containerization. Definition: containerization is a lightweight, portable, and consistent software packaging that includes application code and all its dependencies. The key components that the exam might cover: three major elements. Container images. These are lightweight, standalone, executable packages that include everything needed to run a piece of software. Container runtime. The software responsible for running containers. And orchestration platforms, tools like Kubernetes, that manage deployment, scaling, and operation of containerized applications. The benefit that the exam might cover: consistency across all environments. Containers run the same regardless of where they are deployed. Rapid deployment. Containers can be quickly spun up and torn down. Efficient resource utilization. Containers share the host's OS, making them more lightweight than, say, virtual machines. And improved scalability. Containerized applications can be easily scaled by deploying more containerized instances. Security considerations. The exam will address several. That includes image security, ensuring that the images are free from vulnerabilities and malicious code. Runtime protection, securing the container environment during execution. Network segmentation, isolating containers to minimize the impact of potential breaches. And access controls, managing permissions and authorization for container management. Top associated risks. The exam can cover a number of these, including vulnerable container images. These are using images with known vulnerabilities or malicious code. Escape vulnerabilities, flaws that allow attackers to break out of a container and access host systems. Misconfigured orchestration platforms, security weaknesses in container management tools, and unauthorized access to host systems. A compromised container could lead to a broader system access. The exam presents the scenarios that require understanding of how containers interact with the other concepts we've discovered. 3.5.11 Serverless computing. The definition: serverless computing is a cloud computing model where developers focus solely on code, with the provider managing all infrastructure, including automatic scaling at the function level. So it's similar to PaaS, but PaaS does not typically include the scalability. Other key differences between serverless and our classical platform as a service computing include granular scaling. Serverless scales down to individual functions, while platform typically scales to the entire application. Pay per execution model. Serverless charges based on actual function executions, where PaaS often charges for allocated resources. An event-driven architecture, serverless functions are typically triggered by events, unlike always-on platform models. The benefits, the exam could cover a few benefits of serverless, including near zero infrastructure management. Developers can focus solely on code without worrying about any other server maintenance. Automatic scaling. The platform handles your Kubernetes type kind of thing. And potential cost savings, well, you're only paying for actual computed loads. Top risks associated the exam might look for. Vendor lock-in. Difficulty in moving applications between different serverless platforms due to the vendor-specific features. Cold start latency. Delays when initializing an idle function, which can impact application performance. Limited execution duration. Restrictions on how long a function can run, which may not suit all types of applications. And challenges in security monitoring and testing. Traditional security tools might not be effective in serverless environments. The exam often presents scenarios that require you understand how serverless computing interacts with other concepts we discussed here, such as cloud and other principles. 3.5.12 Embedded Systems. Definition: these are specialized computing systems designed to perform dedicated functions within larger mechanical or electrical systems. The characteristics that the exam could cover: they are resource constrained. These resources usually have limited processing power, a lot like our IoT. In fact, many of our IoT stuff are embedded systems. Real-time operation: the embedded systems must respond to inputs immediately with strict timing constraints. Long-term deployment: embedded systems are often designed to operate for extended periods, many years, without any user interaction. And limited user interfaces: these embedded systems often have minimal or no direct user interaction capabilities. The applications might be various. Again, consumer electronics devices like smart TVs, digital cameras, and other smart appliances are IoT type stuff. Automotive systems, right? All over your car are embedded technologies, embedded things. Medical devices, industrial control environment, again, our SCADA systems. Top risks associated, well, the exam addresses a few of them, and that can include the firmware vulnerabilities. This is a weakness in the low-level software, and not too many people patch, whatever their smart heater as fast as they patch their laptop. Limited update capabilities because of that whole problem. Physical tampering, the risk of unauthorized access or modification through direct physical access to the device, and the potential for use as an entry point. I remember there was a case where they got into a hotel because of a smart thermometer. So the exam, again, will test your understanding of how this interrelates to the other concepts. Again, it's not just one piece. 3.5.13 High Performance Computing. Definition: systems that use very advanced resources to solve very complex computational problems, like our AI friends, right? Key components the exam might cover will include parallel processing units, that's multiple processors that work together on the same problem. High performance interconnections between these processors. Specialized software programs that are designed to leverage the parallel processing capabilities. And optimized storage systems, that's high capacity, high speed storage solutions. The applications can be vast: scientific simulations, weather forecasting, stock markets pour tons of money. I come from a trading background. I know how much they spend. Any big data analytics, and of course, artificial intelligence. We're watching huge demands for these. The top risks associated could include data integrity issues, ensuring the accuracy and consistency of data. Unauthorized access to sensitive computations, then we'd need to protect those high-value research and proprietary algorithms. Resource abuse by malicious purposes. You hear about people doing crypto mining at work or whatever. And potential for cascading failures, managing the risks of system-wide impacts from failures in these interconnected systems. 3.5.14 Edge Computing Systems. Definition: it's a distributed computing paradigm that brings computation and data storage closer to the location where it's needed to improve response times and save bandwidth. Key characteristics that you may see on the exam: reduced latency. Processing data closer to where it's needed minimizes delay in data transmission. Bandwidth optimization. By processing data locally, edge computing reduces the amount of data sent to central servers. Improved reliability. Edge devices can continue to function even if the connection to the central system is disrupted. And local data processing and storage capabilities, edge devices can analyze and store data without always relying on cloud or central systems. The applications that might show up on the exam: IoT devices, content delivery networks, that's caching and serving content from locations closer to the end user. Automated vehicles, rapid processing of sensor data for immediate decision making. Industrial automation, real-time monitoring and control of manufacturing processes. And augmented and virtual reality, providing low-latency experiences by processing data closer to the users. But the top risks associated that the exam is very likely to test you on: physical security vulnerabilities. Edge devices may be located in a less secure or publicly accessible environment. Diverse attack surfaces. The distributed nature of edge computing creates multiple potential entry points for the attackers. Data privacy concerns. Sensitive data processed or stored on edge devices may be a risk if not properly secured. Challenges in maintaining consistent security. Ensuring uniform security policies and updates across all edge devices can be very difficult. And increased complexity. Managing distributed edge infrastructure can be more complex than centralized systems. The exam often presents scenarios that require understanding of how edge computing and distributed systems work together. 3.5.15 Virtualized Systems. Definition: virtualization is a technology that creates multiple simulated environments or dedicated resources from a single physical hardware system. Now, the hypervisor types: type 1 is sometimes called bare metal, runs directly on the hardware without the need for a host operating system. I don't do that. I just use my virtual box, which is a type 2, which runs on top of my either Linux or Windows systems, a host operating system, and then it adds additional layers between the hardware and the virtual machines. The benefits: the exam will highlight several advantages of virtualized systems: improved resource utilization. Multiple virtual machines can share resources of a single physical machine. Easy management or easier and provisioning. Virtual machines can be quickly created, cloned, and moved to other physical locations. And enhanced disaster recovery capabilities. I do it all the time. Virtual machines can be easily backed up and restored. Top risks associated that you'll see on your exam: VM escape. That's the biggest risk, where we figure somebody can get out of one virtual machine, and if there's a flaw in the hypervisor, that allows them to break out of that, sometimes called hyperjacking. Other hypervisor security flaws: vulnerabilities in the hypervisor itself, especially critical in type 2 hypervisors because they rely on the other operating system. Resource contention issues: performance problems when multiple VMs compete for the same physical resource. And challenges in monitoring inter-VM traffic. There could be some difficulty in observing and securing the communication between these VMs. The exam often presents scenarios that require how virtualization works and interfaces with the other technologies we discussed here, especially in the cloud and infrastructure as a service. Whew, this was a long one. So as we summarize this thing, let's recap a few key points. All right. Key takeaways: understand the unique vulnerabilities and mitigation strategies for each type of system we discussed here. Recognize the interconnected nature of modern IT architectures and how vulnerabilities in one area can affect others. And be prepared to analyze complex scenarios that involve multiple concepts from various techniques and technologies we discussed here. All right. Now remember, on our next slide we've got our AI prompt, and you've got to be an AI whisperer for the class and for your job. All right, I hope you're ready to try out your knowledge here and play with the prompt. And I hope by now you've been playing with it a lot, and you may have noticed that sometimes they go off a little bit. Part of your job as an AI whisperer is knowing how to write them. So again, put these skills to use as you interact with the prompt. If the AI starts to drift off topic, guide it back using a clear, concise instruction. No, it's just supposed to be about this, type of thing.